Hello students and welcome to this video lesson. Today we're going to be doing section 2.3. It's the third day and we're going to put a bunch of transformation things together. So for instance, we're going to be doing domain and range and we're going to be writing equations based on the transformed parent function. So let's start with this example here. It says sketch a graph that has a domain from 0 to 4 and a range from -1 to 1. So I just made up a random graph. It could have had a bunch more squiggles in the middle or whatever. So this was a pretty basic one. And the question is, what is the domain and range after we do the following transformations? So in this one, f of x minus 2 plus 1, what that does is that's going to move it right 2 and up 1. There's our explanation. So what does that do to domain and range? So if I actually try this, I move it right 2, so about there, and I move it up 1. So now I'm looking at this orange graph. Well, so the domain is side to side, so that's actually from 2 to 6 now because I moved it right 2. That's the only part that affected that. So domain is from 2 to 6. The range, the only part that affected that was the up 1. So if I go up 1 from each of these, -1 moves up to 0, 1 moves up to 2, so it's from 0 to 2. Here it is. All right, let's try the next graph. So f of -x. So this is a horizontal flip, which actually means, let's reset it here, I'm going to flip it over the y-axis. So remember, it's always opposite of what you think it should be. So if I flip this, let's try this, flip it left and right. Here it is. It's flipping over the axis. So it's actually going to look like this because horizontally it changed. So what is the domain and what is the range now? Well, hopefully it's obvious that the range actually didn't change. It's from -1 to 1, but the domain switch signs, because if you think about this negative right here, it changed the horizontal. And so let's show my work here. So it flipped over the y-axis. We talked about that. The domain is actually -4 to 0 because it's, instead of being on the right side, it's on the left side, and the range did not change. Good. All right, let's try another example. All right, here's another one. So exact same graph and two different transformations. So let's look at this first one here. This 4 is going to be a vertical stretch of 4. And so I'm not going to actually draw it in, but if you think about stretching vertically up and down, so which is going to be affected, the x or the y? Well, it's going to be the y. And so the 1 is going to come all the way up to 4, and the -1 is going to come all the way down to -4. So it is a vertical stretch by a factor of 4. So the only thing that is affected is the range because the domain is not changing. There was no horizontal change. There was only the vertical stretch. So it makes sense that only the range is going to change. So the range got times by 4. All right, this one, well, we know inside parentheses is a horizontal change, and the horizontal is always opposite of what you think it should be. So this is actually a stretch of 3. So it's a horizontal stretch of 3. So looking at this graph, oh, I think I have a graph for this one. Yep, you didn't see the answer. Shh. All right, here it is. So here's my graph. It's 3 times wider because of the horizontal stretch, times 3. So, looking at the graph, the 4 became the 12, the 0 stayed to 0. So the domain changed this time because, again, it's horizontal, and the range did not change because that never had a vertical stretch, a vertical shift, or anything like that. So the domain is 0 to 12, and the range stayed the same at -1 to 1. All right, so that was the first learning target. The next one, we're going to spend some time on working on equations. So we're going to write equations based on the transformations with vertical stretches based on the a's. We're actually going to use points on the graph, kind of like we talked about in yesterday's lesson. So there's two graphs here. Let's look at this one first. So it says identify the key point and another point. That's already done. We have the origin here, and then I found another one here at 1, 4. So hopefully it's obvious what those points are, so you don't have to just make one up. So in this graph, we know this is an absolute value function, and we see that it's not transformed either direction, up or down. And so the basic general equation is going to be something like this. So we have that a in front because that is the vertical stretch. So we know that it's stretched. Now, it might be pretty obvious in this case that it's 4, but it's not always going to be obvious, especially when it's a fraction. So we're going to solve it plugging in this coordinate. So we're going to plug in 1 for x and 4 for y. There it is. And you should be able to solve for a pretty easily. The absolute value of 1 is 1, divide by 1. You should be able to get a is 4, and then plug it back in. So my general equation is y equals 4 times the absolute value of x, which makes sense because if you look back at the graph, it is a vertical stretch of 4. This graph is going to be a little less obvious, especially since you notice on this one, this was 1 over 4 up. This is 6 over 4 down, I guess, from here. So let's do this equation. So again, we know it's the absolute value, and everything besides the vertical, I realized is it's moved up 1. And you might say, I know it's negative, but we'll take care of that later. So my general formula is going to be y equals a absolute value of x plus 1, just because it moved up 1. You want to do the side to side or the up and down, and everything else will take care of with the a. And so here's my coordinate. That's nice and easy, 6, negative 3. So we'll plug 6 in for x, negative 3 in for y, and solve for a. Okay, subtract 1, divide by 6, and we actually get that a equals negative 2/3, which, like I said, is compensating for the fact that it's going down, so it makes sense that it's negative. So plug it back in. There is your final answer. Y equals negative 2/3 absolute value of x plus 1. Alright, so at this point in the lesson, everything else is going to be repeat, repeat, repeat. So let's just try it with some other graphs and see if it makes sense. So we have some parabolas here, which again means my parent function is going to be the x squared. Ignore the vertical or horizontal stretches. Let's just look at that key point right here. So it's at the origin, which means there's no transformation. So the general equation is just an x squared. So we have our a in front. Alright, and once we have our generic function, we're going to plug in our values. So up above here, we had this point, 8, 4. So 8 goes in for x, 4 goes in for y. Let's try it. So 8 squared, 64, divide by 64. Here it is. So a is 1/16, so plug it back into the equation. Alright, let's try it again. So this one's a little bit harder because you'll notice that there is a transformation vertically and horizontally. So let's write the general equation using this as our normal key point. So this means that it was transferred 3 to the right and 5 down. So that means it's going to be an x squared with a minus 3 in the parentheses and a minus 5 on the end. So again, this compensates for the to the right 3, and this is for the down 5. And then you just pick another point. So this one is for negative 3. So 4 in for x, negative 3 in for y, and we will solve for a. There it is. 4 minus 3 is 1. 1 squared. Make sure you do order of operations, so it's really 1a. We'll bring the 5 over, and a is just 2. So make sure to put the 2 back into your general equation back up here. So all it is replacing a with 2. All right, a couple more examples, different transformation graphs. So let's start with these ones. So these are our swimmer's arms, which means our square root of x functions. And this is not transformed either vertically or horizontally because it starts at the origin. So there's our generic function. Let's plug 2 in for x, 5 in for y. It gets a little gross on this one. Okay, we'll divide by square root of 2 on both sides. So you can leave it like that and just plug it back in. I know that's not proper, but that's as much as I care. That's fine. All right, and this one. All right, so it's a swimmer's arm again, but it is transformed down. Down 4, in fact. So that's going to be a minus 4 on the end. But notice normally a swimmer's arm goes off to the right. So since it is reflected over the y-axis, it's actually a horizontal flip. And so it's going to be a negative x inside the square root, so inside the parenthesis if you want to think of it like that. But we don't know how much is stretched vertically, so we have that a in front. So then we'll use this other point. Again, it's not the bottom point. So negative 4, 0. So negative 4 in for x, 0 in for y. You'll notice we get a negative negative inside. So really that's just square root of 4, which is 2. So we have 2a minus 4, solve for a. Bring the 4 over, divide by 2, a is 2. So going back up to here, we have that 2 in place of a. Everything else stays the same. Final answer. All right, one more slide. So this graph right here is the x cubed graph because it goes up really fast instead of being a cube rotograph, which would be more flat. And this one's kind of hard to see, but this is what we call the point of inflection because it changes from going down to going up. So this would be the point of 2, 0. So that means it was transferred over 2 to the right. So in my cubic graph, that is going to be minus 2 inside the parenthesis. So the generic graph, or equation, excuse me, is a in front of the minus 2 cubed. This is our coordinate 5, 1, so we'll put 5 in for x, 1 in for y, and solve. So 5 minus 2 is 3. 3 cubed is 27. And we will solve. So a is 1 over 27. So plug it back in. So we have 1/27 x minus 2. All right, and so that is our final example for the lesson today. Oh, we actually have a handout for you on this one, so you don't have to actually draw them from the book. They are book problems, but it is on a handout that the teacher will give you. Have a good day.